Hello everyone, my name is Anish, and today we'll be talking about how to tend and tune your multi-agent reinforcement learning experiments with array and weights and biases. So another way to give that name is scaling production-grade reinforcement learning. So a few examples of multi-agent reinforcement learning that you're probably used to seeing in your day-to-day are shown over here. The two main ones that I'm going to talk about today is drones, and that's drone delivery specifically, but the management of how to communicate with agents of drones, and also autonomous vehicles. So first, let's talk about what is multi-agent reinforcement learning for the folks who don't know. So as you can imagine, and the name implies, a single agent reinforcement learning experiment is when an agent, someone acting upon an environment, acts upon this environment, and then this environment learns from the reaction of this agent. So there's this one-to-one flow of a person acting upon a thing and that thing learning from that reaction. Now when you incorporate multiple agents in this scenario, you're faced with a much more complicated process. You're faced with the complexity of every single agent affecting upon this environment, and as a result, the reaction of this environment must incorporate and give credit to the right agent. So that's a lot of details that you must manage for every single individual agent that you pull in this multi-agent environment, and you must also manage this environment itself. So as you can see here, this complexity of the environment causes an innate need for more computation, and also with the heuristics that we use for a lot of this multi-agent reinforcement learning experiments, there's a problem of trying new techniques to learn for the agent or exploiting techniques that tend to already work for a specific action that our agent wants to take. And the problem is that if we don't take into account these specific complexities, you run into problems where your Tesla thinks a horse-drawn carriage is a truck. And so when these situations occur, you need to ensure that you also have an ML platform that's able to quickly grab this specific problem, iterate upon it, and then release that fix quickly upon the world. So these are 5 tenets that you can use to categorize and organize this. But I think that deep down, you want to minimize the refactorization problem for machine learning practitioners so that they can reduce the amount of friction in both their development experience and their production experience. Because at the end of the day, we want these agents to do things. We don't want just our autonomous vehicle simulation to live on our computer. We want to make sure it actually works in the cars that we want to use in the world. And so in general, there causes 2 fundamental challenges with ML training. The lack of scaling from the hardware resource management side, which Ray helps to solve, and then the MLOps side, a very complex network to provide workflows that make the most sense for your team and your machine learning workflow as it relates to your project. So in the case of handling the resources for these multi-agent reinforcement learning experiments, we have RLLib. So the Anyscale and Ray's library for managing reinforcement learning experiments. And we also have weights and biases, a developer-first MLOps platform that hosts a suite of tools to make the ML training process really easy, and then now the ML monitoring process extremely easy. And so what you can do is we provide tools to make it very easy for you to visualize, track, and debug your model pipelines in weights and biases, while also ensuring a full connection to not only Anyscale from weights and biases side, but from Anyscale to weights and biases. So you have this dual connection to easily go to the right dashboard as it relates to your need in hardware investigation versus ML management and ML investigation. And this is all easily done with a single line of code by simply adding in the WANDB logger callback to either your Ray train or your Ray tune experiment, and with a simple flag such as save checkpoints equals true, all of your model checkpoints and all of your model metrics during training will become centralized in one repository, which I'll show you soon. So to give you kind of a mental model of how to think about this type of workflow is at the very top, you have almost the UX layer for the modeling experience. At the bottom, you have hardware management by Ray, which will allow you to actually scale your experiment on all the resources that you have available to you for your GPUs in your cluster. But then when you want to actually investigate whether your model is working performantly on these GPUs, that's where weights and biases can help. And so to show one specific workflow in this red box, this is a standard end-to-end workflow that you may see in standard machine learning teams. So let's talk specifically in the case of autonomous vehicles. So in this case, we'll be talking about taking LiDAR scans from one of those fancy Waymo cars. In this case, actually a level 5 car from Lyft, formerly level 5. We're taking these LiDAR scans and we're projecting it down onto this nice coordinate grid of XY positions over time, but also doing this for every single car in the frame. And we're also understanding the underlying trajectory of the car, so we know whether or not to brake or whatnot. And so a team of your ML engineers may actually look like this. You have data engineers, data scientists, ML engineers, and your ML manager all having stake in this one really critical application, the planning of your self-driving car on a road given the LiDAR scan. And so we want to ensure that all of our GPUs are properly allocated and utilized to the right team. So these GPUs may be separate clusters managed with different scales of A100s to simple Tesla T4s. And more than that, a lot of these flows impact other team members and other steps in the ML process. So ensuring that every single output that is generated from a persona in your ML team and ensuring that you have a central system of record for that information, and then also contextualizing that. So when you do have this horse-drawn carriage mistaken for a truck, you can directly click into the model and understand where that happened. So let's do that. So in this specific example, you can see that the blue marks here represent the prediction of the self-driving car, while the pink marks represent whether or not what the true intention of that car was. This model does horribly. If we were to drill down into specific, drill down too much. Drill down into specific frames, you can see that for stationary scenes, aka where all of these cars are currently parked at a red light, stopped at a red light, this one blue car is predicted to run into the green car. And so that's a problem. We can't deploy this model into production. So let's work backwards to see where the flaws occurred. So we can actually drill into this current model we have in production here and click into and see the actual underlying training process. So you have access to all the model checkpoints, the configurations, the underlying system utilization over all of our GPUs. But more importantly, let's actually see if something looks wrong in our loss values. We could actually go in and see underlying, for our loss, are we reaching kind of this this underlying U-shaped curve? And was there any spikes that look wrong? In this case, this looks pretty consistent, so that we would expect from the loss values of our car. So then we look into our actual evaluation process. So we have the ability to, in context, understand not only the outputs of the model itself, but we actually drill down into the comparative analysis of all of our different models centralized in one location, and we're able to perceive and see what the loss is across for these different models, and also drill down and see directly the predictions that I showed you earlier. And so that is one investigation of, that is one showing of how to use the dashboards to look at the central comparisons that you did to evaluate that single model for production, and also the training metrics that underlie the process for this specific model. So to recap, you have the in-context data alongside the resultant training of all the hyperparameters for these models itself. So you can drill down and debug your model really holistically. Next, we also have this similar situation for multi-agent reinforcement learning for quadrotors, aka the drones that you can imagine picking up your packages and in the future dropping them off in your front doorstep. And so in this process, it's a very similar workflow that we see here. In this case, we'll be looking only at the blue box here, which is training exclusively. Before, we looked at training, data prep, and evaluation. But over here, we're just looking at training. So in this case, we're looking at leader-follower drone flight patterns, aka where we look at one specific drone in our collection of drones and say, follow this one drone as the leader and build formations or associate your movement patterns based on this central drone. So we use a tactic called PPO to actually do this, this loss calculation to understand whether or not our drones are all learning properly and making sure that this learning process is incremental. And we use this technique called decentralized actor, centralized critic. And so what this means is that we have all of these drones independently working from each other. They aren't aware of each other necessarily, but we have a centralized model that is essentially able to know the position, location, and intent of each of these different drones. So by having this centralized critic model coordinate the efforts of these independent drones, we're able to then use PPO and this concept of leader-follower to really get this full workflow of how to teach our drones to go and actually follow this, this pattern that we're proposing. And so nicely enough, RLLib, which is the reinforcement library that Ray provides, makes a lot of this process for environment management via GIM, so that first green block over there, and also the modeling process, very easy to plug into Ray Train and Ray Tune. So another example of this dashboard, which uses the same workflow I showed you earlier, the one where we just simply add in that one line to the logger callback into a RayTune experiment, and you have a very similar dashboard. We're able to compare all of our experiments for this drone flying concept and also relate it directly into any resultant videos that we may want to generate. So this is a really far away one. I haven't worked out properly how to use the camera management in this specific environment, but if we were to zoom in, you can see that these specific black dots are the drones that are flying in context. And what's nice about this workflow is one configuration we can do here is massively scale up the amount of agents in our environment, and that does not change a single aspect of our modeling process. And so to recap, some of the considerations that we have here is we want to ensure that we can have visualizations that make sense for our environment, have that centrally located in one system of record for our ML team, and ensure that we can easily iterate upon the different configurations that matter for these different agents in these environments that we're building out. And so before I leave, I do want to propose a cool concept that I've been hearing a lot about, and that's LLMs, something you guys probably haven't touched yourselves. And so I think there's a really interesting concept of generative agents that's coming out right now. The ability to use LLMs to be this main core of these different autonomous units of logic that communicate with each other. That sounds like an agent in an RL environment. So why don't we combine the concepts of these LLM-based agents with these dynamic environments that RL provides and create generative reinforcement agents? If someone's going to go out there and build that environment, which I think is coming soon, we offer new tooling to also ensure that Anyscale endpoints, the tooling that you may use to build these LLM models, can also work with these RL workflows that I showed earlier and your LM workflows by honoring monitoring and debugging processes. And so this is our ML platform. Thank you.